everyone, welcome back to my channel, The School Wiz. I am Hafsa Rashid and I am here to talk about a topic of physics called waves. Well, waves is a very interesting topic, and in my previous video, I gave you guys an introduction on what a wave is and how many types of waves are there in general. Well, in this video, I will cover up the properties and characteristics of a wave. Well, in order to understand what a wave is, you need to first of all understand how the waves behave in different kind of situations, and for that you need to understand the characteristics in depth. Well, waves, to be honest, we are surrounded with waves, and we are surrounded with different kinds of waves around us. It could be light, the sound, and many more. Well, there are some basic characteristics of waves, and those are its frequency, speed, and its amplitude. Well, when I talk about frequency, I mean that how much time it takes for one complete wave to form. If a wave forms in a very short amount of time, that means it has a very high frequency. You can use the formula F is equal to N by T, where N represents the number of oscillation or a number of one cycle, and time represents time period for that one complete oscillation. And amplitude is how much that one cycle deviates from its equilibrium position. If the amplitude of the wave is larger, in terms of sound, we would hear a very loud sound. And if the amplitude of that wave is going to be shorter than the average, then we're going to get a very low loudness sound or a very quiet sound. Well, in terms of sound, if I relate frequency, if at a very short time a wave completes its cycle, that it has a very high frequency, and that would mean you're going to hear a very unlikable high frequency pitched sound. So another important property of wave is its speed. Speed, we all know, is a kind, what it really explains us that how fast an object travels or how slow an object travels. So wave, since it carries energy from one place to the other, it's very crucial for us to know that what its speed is. So the speed of the wave is determined by two factors: the frequency of the wave and the wavelength of the wave. We have previously discussed about frequency, but about wavelength, what really is a wavelength? Well, wavelength is nothing but the distance between two similar points in a wave, or in simple terms, we could say that wavelength is the distance traveled in one complete cycle or one complete oscillation. So when you have to determine what factor governs speed, even though the equation of the wave speed is frequency into wavelength, when we have to compare between what governs the speed, then we have to keep one of the quantities constant. If you keep frequency constant, then wavelength consecutively varies with the speed. So if you increase the wavelength, then you increase the speed of the wave. If you keep wavelength constant, then the speed varies proportionally with frequency. In order to understand the derivation, we will look into a mathematical expression.
The graphical expression of a wave is similar to a sine curve, as it involves repetitive movement. The paths of the sine curve demonstrates unique properties that is carried by a wave. The properties involves amplitude, wavelength, frequency, and wave speed. In the sine curve, the highest most position is stated to be the crest of the wave. Consecutively, the lowest most position is stated to be the trough of the wave. Amplitude is the property that tells us the displacement of a wave from equilibrium position to the highest most point. The amplitude of the wave also suggests us how much energy that wave is carrying. Wavelength, on the other hand, is the distance traveled by a wave in one complete oscillation. It is also the distance between two crests and two troughs between two adjacent cycles. frequency is the number of oscillation per unit time taken. It tells us how much time it takes for one complete oscillation to end. If the time taken for one complete oscillation to end is smaller, then we say the wave has a higher frequency. If the time taken is longer, then we say the wave has a lower frequency. Hence, the relationship of time and frequency can be suggested using this formula: F is equal to capital N divided by capital T, where capital N represents number of cycles or oscillation, where capital T, on the other hand, represents the time period for that number of oscillations. Wave speed is in generally tells us how fast or how slow the wave will be traveling. Wave speed in general has the formula of wavelength into frequency. We know that speed is equal to distance divided by time. For a wave, the distance traveled by one complete oscillation is stated to be the wavelength. If we take time aside and if we write it as 1 by t, 1 represents number of oscillation and time represents the time taken for that much oscillation. So 1 by t here denotes to be the frequency. Hence, wave speed has a formula that can be derived as v is equal to f into lambda. The equation v is equal to f lambda can be used in several ways. In any kind of equation, when we take one of the variables to be the constant, a relationship develops between the next two variables. Here, if we take the frequency to be constant, then wavelength varies proportionally with the wave speed. This happens usually in a characteristic of a wave called refraction. If we now take the wavelength to be a constant factor here, we can vary speed with frequency. On the other hand, if we take speed of the wave to be a constant, then we can vary and we can say that frequency is inversely related to wavelength. This relationship is seen in electromagnetic waves. In electromagnetic waves, they travel with the speed of light, which is 3 × 10 to the power 8 meter per second. Since the speed is a constant factor here, frequency is inversely related to the wavelength. The most highest wavelength has the lowest of frequency, which is the radio waves, and the wave in that spectrum having the lowest wavelength has the highest frequency.
So far, we have discussed about the main characteristics of the wave, which were the speed, frequency, and wavelength. And we have also discussed how their alterations might vary with the wave and whatnot. Well, now we will be discussing about the property. It's very essential to know about the properties because waves can behave differently in different kind of situations. The properties include reflection, refraction, diffraction, and interference. Reflection, which is the simplest one, and we get to encounter that in our daily basis. So reflection is basically as simple as that when you walk in front of a mirror, what you see is your reflection of yourself. That happens because light falls on you, that reflects from you to the mirror, and there you go, you get to see yourself. If I have to explain it in the form of a ray diagram, then I would say that when light hits a smooth barrier or a smooth surface, it hits that surface with a certain angle, and that angle could be stated to be the angle of incidence, and it reflects off that smooth barrier with the same angle, which is known as the reflected angle. So what we can demonstrate is that the reflected ray, the normal, and the incident ray, they all lie on the same plane. Normal is nothing but an imaginary line that is pictured usually between the interface between two barriers. So the first law here is the incident ray, the reflected ray, and the normal, they all lie on the same plane. And the second law of reflection is that angle of incidence be equal to the angle of reflection.
When light is reflected from a surface, it obeys the laws of reflection. The laws of reflection suggests that the incident ray, the reflected ray, and the normal to the mirror at the point of incidence all lie in the same plane. And the second law suggests that the angle of incidence must be equal to the angle of reflection. This can be demonstrated using a ray diagram. In a ray diagram, if you keep an object and an observer at one side, and if you want to view the image on the mirror side, what really happens is that we get to see the same image. That is because when the light from the object hits the mirror, the ray that hits the mirror is said to be the incident ray. That ray is reflected from the mirror surface as a reflected ray to the observer's eye. The angle of incidence that connects with the normal line is said to be the angle of incidence. And the angle that connects between the ray of reflected ray and the normal is said to be the reflected angle. The angle of incidence is equal to the angle of reflection. Normal is a line that is imaginary, but it is perpendicular, which connects the two interfaces together. This property enables us to understand how the light is reflected and how it depends on the nature of the surface. If a parallel beam of light is incident on a smooth or polished surface, it is reflected as parallel beam, which is stated to be a specular or a regular reflection. Most surfaces which appear to the naked eye to be smooth are in fact quite rough, as it can be seen when they are viewed under a microscope. Hence, when parallel beam of light is incident on a rough surface, since the surface is not smooth, the rays strike the surface at different angles. Therefore, the angle of incidence varies. They are reflected at many different angles as well. This kind of irregular reflection is known as a diffused reflection. Most objects are rough, and so the reflected light that reaches the eye is diffused. They therefore appear to be dull rather than shiny.
The second property is refraction. Refraction is basically the change of the wave, how it behaves when it travels from one medium to the other. Some of the characteristics of the waves changes when it moves from one medium to the other. Those are speed and wavelength. Now, in order to simplify the understanding behavior of the refraction, well, let's imagine that on a table you have taken a glass and you've poured some water in there, and you've placed a pencil or a pen of your choice. What you would see that the part or the portion of the pen or the pencil above the water level is exactly the same as it was before in the pen stand, and the one that is below the water surface is slightly bent in shape. Now, while you were seeing that, why was that happening? Well, around us, whatever we see, when light falls on it, it reflects from that part. And when light reflects, we get to see that. So when light was hitting the pencil, which was above the surface of the liquid, we saw that exactly the same way usually we see it in a pen stand. But when light was hitting the portion that was below the water level, well, light had to travel through the air into the water medium. It had to cross two medium. Now, when it had to cross two medium, the two characteristics got changed. One was speed and the other one was wavelength. Since air is the medium where the particles are spaced out, that's the less dense medium, and the water medium where the particles are slightly packed, then the air medium is the denser medium. So, since earlier when we were trying to derive the relationship between wavelength frequency and the speed, I have already stated that in order to determine the relationship, we have to keep one of the quantities constant. Now here, what remained constant throughout this entire refraction process was frequency. So if you keep frequency constant, you get to see the relationship between speed and wavelength, which is proportional. So when the light was going from the lighter medium to the denser medium, the speed decreased because the wavelength decreased.
Refraction is the bending of light as it crosses the boundary between two media at an angle. This deviation of the ray occurs because light travels at different speeds in different media. However, when the light hits the barrier or the interface between two different media at 90 degrees or normally, no such deviation is observed. Rather, the light happens to travel at a straight line. Although the light is not showing any kind of deviation, two changes are still taking place. Let's say we are comparing between the ray of light entering the medium between air and water, and we are projecting the light exactly at 90 degrees in between the two interfaces. When light enters from a less dense medium to a more dense medium, the wavefronts become closer together at the denser medium, which also makes the light slow down. This behavior can be mathematically explained using the equation wave speed is equal to f lambda. As we have discussed earlier, if we keep one of the variables constant in the equation, we can develop a relationship between the two other variables. In this case, in refraction especially, keeping the frequency constant, wavelength becomes proportional to the wave speed. Since the frequency of the wave is kept or held constant, wavelength becomes proportional to the wave speed. Hence, when the wavelength after reaching the denser medium decreases, the speed also happens to decrease. When a ray of light hits the interface between air to water medium or air to glass medium, that light emerges out of that water medium at a different angle. This happens due to the property of refraction. As a ray of light was traveling from a less dense medium, let's say the air, to a more dense medium, the angle has changed. The angle, in other words, has decreased. Why did it happen? Let's focus on the angles. When a ray of light was incident initially at the interface, the angle that made with the normal and the incident ray was known to be the incident angle. And the angle that makes between the normal and the refracted ray is said to be the refracted angle. As the wave train was entering from a less dense medium to a more dense medium, the wavefront was getting closer to one another, which caused the wave train to become slower. As the speed decreased, it caused the wave train to bend towards the normal, hence decreasing the angle. Due to the changes in speed between two different media, the angle has also changed. In order to understand the relationship between these two changes due to the change in media, we take in consideration of Snell's law. Snell's law states that the ratio of sine I to sine R is a constant, and it is denoted as small n, which is known to be the refractive index. The refractive index is a constant for a given pair of a media, and it is also defined to be n is equal to c by v, where c is said to be the speed of light in air and v to be the speed of light in the medium. Both these equations can result in similar ratio for the similar amount of pair of media. Let's see a scenario where the situation is a little bit of reversed. Now, the light could enter from a denser medium and it could emerge out from the less dense medium. Let's say we have taken a ray of light and we have made that light go incident into the denser medium. The incident ray hits the interface and connects to form an angle of incidence at the denser medium. That ray bends at a different angle and comes out from the less dense medium. Whenever the wave train is moving from a denser medium to a less dense medium, the wavefront distance increases. In other words, the wavelength of the wave increases, which also consecutively causes the speed of the wave to increase. Since the speed of the wave train at the less dense medium increases, light happens to bend away from the normal. If we keep on changing the angle of incidence in the denser medium, light will keep on moving away from the normal. Therefore, the angle of incidence in the denser medium, at which the refracted angle happens to be 90 degrees with the normal, is said to be the critical angle. Critical angle is the angle at the denser medium for which the refracted angle happens to be 90 degrees. If we further increase the angle more than critical angle in the denser medium of the incident ray, then the light happens to reflect back into the denser medium. This kind of phenomena is known as the total internal reflection. Total internal reflection requires two conditions. The first condition is such that the light must enter from a denser medium and it must be traveling to a less dense medium. The light that is incident on a denser medium must be or must have an angle greater than the critical angle. Only if these two conditions are met, the total internal reflection can occur. Now that we have precisely looked into the details of how the wave train behaves when it moves from a less dense medium to a more dense medium, and also from a more dense medium to a less dense medium, and how their properties also changes. This comparison, however, changes between the comparison between the water waves at the shallow end and the same water waves at the deeper end. When we're talking about water waves between shallow to deep water, the wave train, however, behaves a little differently. The speed of the water wave does depend on wavelength, but it also depends on another factor. It depends on depth. As the depth of the water waves at the deeper end is higher, the wavelength and the speed also increases at the deeper end. Consecutively, as the depth of the water wave is smaller at the shallow end, the wavelength and the speed decreases at the shallow end. Hence, water waves traveling from a shallow end to a deeper end would travel faster than it would otherwise.
The third property of the wave is that diffraction. Diffraction is basically when the wave approaches a gap or a barrier, it spreads into geometric shadows. This happens with every kind of wave. Well, the diffraction pattern or the deviation after the wave passes through the gap depends on the aperture size and the wavelength. When diffraction happens, the speed, wavelength, and frequency or amplitude, it doesn't change. And the diffraction pattern, whether a wave will diffract or not, depends on the aperture size. If the wavelength and the aperture size is similar, then that is the first point where you're going to observe a diffraction. Well, that is why even though we get to understand what diffraction is, but when we take a torchlight and put it through a door hole, what we don't see is the light can't reflect. Well, light has a very, very low wavelength. Therefore, to make the light diffract, we have to make that aperture size equal to that of the light's wavelength, or it has to be shorter than that. So in order for diffraction to be observable, the wavelength of the approaching wave should be equivalent to the gap size, or the gap size should be shorter than that. That is when we will get maximum diffraction. So that was all about the properties and characteristics of the wave. I hope you have found this video interactive and informative. If that is so, please subscribe down below for more content like this, and I'll see you guys around.